Optimization of a scheduling system for the production of custom fasteners at the Nord-Lock facility in Carnegie, Pennsylvania. This facility produces Superbolt's line of tensioner and bolting products, including jack bolt tensioners, nuts, flex nuts, and washers. Superbolt has over 5,000 products in their catalog, and the facility consists of a full machine shop with turning, milling, grinding, and metal finishing operations. Superbolt produces a variety of custom and stock orders and also offers 3-day expedited processing for some products. The general process for creating a bolt starts at the saw. Metal is received as bar stock and then cut into appropriately sized blanks at one of 3 saws. Next, the cut blanks proceed to the lathes to be turned. There are 10 lathes in total, and orders are directed to certain lathes based on their size. Most parts are turned twice, once on each side. After turning, the parts need to be milled to create holes. Post-milling, the parts head to the finishing and assembly steps to be prepped for shipping. Currently, Nord-Lock has no standardized system for how orders are scheduled for production on the shop floor. Operators rely on due dates plus their past experience when choosing which order to machine next. With this method, some orders slip through the cracks, making them late. Rush or expedited orders also mess up production because of their very tight time frame, meaning that operators have to neglect standard orders to work on rush ones. Nord-Lock pays for this lack of scheduling in overtime costs. The facility currently runs between 800 and 1,000 hours of overtime per month, and each hour of overtime costs an estimated $35 per worker. This is 1.5 times the normal rate. We believe that Nord-Lock can reduce labor costs and decrease their number of late orders by addressing their lack of production scheduling.
In order to address the scheduling problem at Nord-Lock, the group developed the following action plan. Create a scheduling tool to reduce late orders, conduct time studies and interviews with operators and managers at Nord-Lock, evaluate alternative scheduling rules using randomly generated representative order sets based on historical data, develop a queuing model based on data from router lines to find average queue times, determine and compare the performance of each scheduling rule with the metric of late number of orders within 20 workdays, and perform a cost analysis based on wage and overtime cost.
We decided to create 3 different scheduling tools: critical ratio, first in, first out, and earliest due date. The critical ratio is calculated by finding the total time that the order spends in the system and then dividing that by the time until the order is due. In Nord-Lock's case, this means the sum of the cycle times, setup times, and time spent waiting in a queue divided by the number of days until the order is due. The critical ratio algorithm is more complex than the other 2 scheduling methods and takes more factors into account when generating its schedule. For this reason, we believe that the critical ratio tool will provide us with the best schedule. The critical ratio scheduling tool was too complex for us to create in Excel. It involved joining tables, summing values based on router lines, parsing out other values, and more. For this reason, the group decided to use Python to create the scheduling tool. The tool uses a combination of Python and SQL to generate the critical ratio. Once the critical ratio is generated, the program then orders the list in descending order based on this number. The program contains line-by-line explanations and documentation to make it more user-friendly and to facilitate implementation at Nord-Lock.
An input that will be required in our scheduling tool is a queuing model. To form this model, we learned that an MGS queuing model most closely represents a manufacturing facility. That is a model with a Markovian order arrival rate, a deterministic order processing rate, and has multiple servers that represent each machine. The model that most closely represented this type of setup was the Pollaczek-Kincan model, or a PK model for short.
The queuing model provides 2 important outputs: the average number of orders in the queue and the average amount of time an order spends waiting in the queue. The average wait time is then added to the cycle and setup times in our critical ratio formula to compute the total time per order.
We now knew the average wait times in queue that would be seen at each of the different machines. In addition, we were also able to identify an extremely helpful piece of information about Superbolt's facility. The saws at the start of their manufacturing process are the bottleneck point by far. This means it would be much easier for us to schedule orders into their system. That is because all subsequent manufacturing processes would theoretically have the capacity to keep up with orders that are passed along to them.
Our team randomly generated a representative data set of job orders based off of an open job orders list from October 2017. A random order program was created in Mathematica. Distributions for the variables such as number of orders open per day, quantity in an order, number of days until the order is due, and the type of part in an order were included. We obtained an acceptably high p-value fitting the data for the number of orders open per day using the normal distribution. For the other variables, we used empirical distributions and random select functions to determine the output for those variables, as it was not possible to infer the probability distributions. For example, some part types only showed up once within the given dataset. Overall, we obtained a plausible list of orders which both mimic the October data while introducing appropriate randomness.
In order to determine the amount of late orders in each scheduling tool, we came up with the simulation model in Excel. We scheduled the 3 saws with a list of over 15,000 open orders for each scheduling tool. After open orders were prioritized, they waited in line at the saws until one of the machines became ready. The order would then be processed at the rest of the machines for the process. Computing how many work hours were available, along with how long was needed to complete each order, we were able to determine if each order would be completed before the due date.
Implementation of this scheduling tool is simple. Simply place the router lines, open order, and queue times file in the same folder as the scheduling tool. Then double-click and your new schedule will appear.
After simulating each scheduling tool based off 20 days of service, we discovered that the critical ratio method produced 95% on-time orders with 89 production hours required. The earliest due date produced 95% on-time orders with 90 production hours required, and the first in, first out method produced 95% on-time orders with 155 production hours required. The yearly cost to run the critical ratio schedule comes out to $107,750. The yearly cost to run the earliest due date schedule comes out to $109,500, and the yearly cost to run the first in, first out schedule is $223,250.
In the end, we found that critical ratio delivers the best schedule of the 3 methods we tried. It's the most efficient and has the lowest yearly cost because of the reduction in the number of overtime hours. We would recommend that Nordlock implement the critical ratio scheduling tool as soon as they can and run a trial period to test it in real time. Surprisingly, we also found that simply scheduling orders by the earliest due date was a close second in terms of efficiency and cost. Earliest due date scheduling is therefore a viable alternative for Nordlock as the critical ratio does not fit their needs. Our final recommendation is to research expanding the capacity of the SAW station in the future. Our analysis showed that the SAW is the bottleneck in the process, and operators at the plant confirmed this. Adding more cutting capacity by upgrading current machinery or adding a 4th SAW could relieve backups in the process and allow orders to be completed more quickly.